So transitioning, kind of switching gears here from the nutrient cycles and nutrient management, I wanted to talk a little bit about some of the factors that govern soil erosion and soil health from a wasting perspective. So one of the things that you'll encounter are to describe the different types of erosion are sheet erosion, rill erosion, or in extreme cases, you start to form gullies. So if you have a channel more than 30 centimeters deep, that's referred to as, you start to form rills and gullies. These would be the more extreme forms of erosion. So these are all just ways to describe how eroded a landscape is. And we have one tool available to us that can predict the amount of material actually leaving a site in tons per acre per year. And that's referred to as the universal soil loss equation. So have you guys heard of this before, especially the engineers? Have you had some exposure to this equation before? I'm seeing more no's than yeses. It sounds pretty impressive, right? It's a universal equation. Sounds pretty awesome. We're going to go over some of the caveats from this equation. Couple things to mention right off the bat. So all of these factors here are multiplied by each other. And I'll go over what each one of these components is referring to. So what that means is if we're missing any one of these components from the model, it won't work because they're all being multiplied together. Also, the error terms with each one of these factors, since it is a multiplicative multiplier model, the error terms also get multiplied by each other. So if you could have really precise estimates for all of these variables, but if one of them was really off, it's going to affect the entire output. So those are some things to consider. Furthermore, this is an empirical model. It's not a mechanistic model. So the numbers that go into it are not actually rooted in reality. They're just statistics. So all of the values that go into here are between a 0 and a 1. And somehow in the calculus or the special sauce of the way that they put this together, it does actually equate to tons per acre per year, but the individual numbers themselves don't actually correspond to real units on the landscape. So it's a statistical model. So we are predicting tons per acre per year, and I don't want us to get too in the weeds about all of the variables. I'll hone in on what I think are the most important, or there is one that's probably the most important. But I think I just want us to understand that when you see this equation in a report, or if you hear about universal soil loss, I want you to think, okay, this is an empirical model that estimates erosion, and there are some assumptions that have to be considered in this. So that's the take home here. And it can be a potentially useful tool, or at least something that you can use to justify a decision that you make in terms of saying, ranking soils and their susceptibility to erosion. This is something that you can use to justify your approach. So the first part of the model is the rainfall erosivity factor. So obviously the more rain we have, the more velocity we have from displacing particles. So areas that have intense rainfall are obviously going to have more susceptibility to erosion than arid climates. The second component is the soil erodibility factor, or K. You probably encountered this value when you were doing the web soil survey exercise. Do you remember seeing tables associated with your series that had erodibility represented as a K? So this is probably the most important variable of the universal soil loss equation, because this is a standalone parameter that you can use to evaluate the susceptibility to erosion of every individual soil series. So you can imagine doing a report for a landowner where you have all of the series provided, and if you want to make some statements about how vulnerable they might be to erosion, you could include this statistic, this K factor. So the larger the variable, generally the finer the texture and the more susceptible it is to erosion. So for example, our Kalkaska sands have a value usually far less than 10% clay, and we have a pretty low K factor. Whereas the Grave Rot series can have as high as 18% clay, and it's a much higher K factor. So broadly, has broad utility in understanding soil structural stability and susceptibility to erosion. So yeah, what do you think?
So the higher the value, the more susceptible.
Yep. So the higher the value, the more susceptible to erosion. And generally, a basement and ceiling range for K values is between 0.2 and a ceiling of about 0.7. So anywhere in that range. So again, the higher the values that we have for any of these components means more erosion because they're all of the numbers are being multiplied by each other. And then again, the net output being erosion in tons per acre per year. So for most of the things, the bigger the number, the higher the erosion. Then we have a combined factor of slope length and steepness. So this is intuitive, right? The steeper slopes are going to have greater erosion, and the longer the fetch, also the more potential energy we have. If we have runoff occurring and it's a longer fetch, it means that we're going to have a greater ability to actually move soil particles. So this factor is actually based on some experimental data. So a lot of the components of this equation were developed in agricultural lands, and the slope length and steepness factor was measured on experimentally on a handful of soil texture types using a fetch of 22 meters and a slope of 8%. So they would basically take water trucks and then try to measure on different texture types how much erosion happened in this 22 meter 8% slope experiment. So the longer the slope, the greater potential we have to go from sheet erosion into the rill or gully formation. And then we have another two-part component, the cover and management practice factor. So this is actually a best management practice component. So there's a management part baked into this equation. And if nothing is done, if there's no mitigation or no activity done to try to mitigate erosion, the management practice factor C is 1. And then if there is anything done, that number actually goes down. So unlike the other components of the universal soil loss equation, this actually reduces the amount of erosion. So if you do something like put water bars in place, or if you do contour tillage, there's a whole suite of different activities that are presented in your textbook. It actually reduces the value from 1 down to some lower proportion. And then that helps to actually make the prediction, the erosion, even smaller. For cover, again, if there is bare soil, there's no cover at all, the value goes to 1. And if there is some sort of vegetation present, the number is less than that. So again, that cover management practice factor is reducing the amount of erosion. So taken together, this equation has 3 general components. It has a climate component, which is represented in the rainfall erosivity factor. It has an edaphic or physiographic component, which is represented in the K factor and the slope length and steepness. So this is kind of representing physiography and soil processes. And then it has a management component or a best management practices component, the cover and management practices factors. So are there some huge assumptions that go into this? Yeah, absolutely. Does it have some utility? I think so. I think it's, it does have some ways to justify a management decision. And it's something that you can use to protect yourself from lawsuits or from, people arguing with you about a certain decision. So if you see the universal soil loss equation provided in a report, if you see this weird suite of characters, A equals Rickelskop or whatever, just know that it's predicting erosion. And I think that the most important component here is, again, the K value, representing soil erosivity. Any questions about that? There's a whole bunch of tools available too. Michigan State Extension has a really cool website that's got a graphical user interface, and you can just plug in values and it'll spit out erosion. There's a variety of tools available, and your textbook has some examples as well. So it might be a fun thing to play with. There's one more statistic that's available to you, and that's the tolerance value. And this is provided in the county soil surveys as well. So there's a different T value for every soil series. And what this is represented, so this is a statistic that was developed in the late 1940s, kind of informed by what was going on with the Dust Bowl. And what this is trying to predict is a tolerable amount of loss that could happen for a given soil horizon. Well, that sounds a little strange, doesn't it? What tolerable? That's kind of a objective descriptor, right? That's not based, that doesn't sound like science to me. It sounds like someone's opinion. Well, the t-value has a couple different things baked into it. It has economics baked into it. So it takes into account how expensive it would be to replenish the mineral nutrients for a given soil type. So there's a value component in here that is based on subjectivity. So someone is assigning a value to a soil based on the mineral nutrient component. It's also based a little bit in the rates of weathering. So how fast a soil horizon could reform. So if soil formation can keep step with the rates of erosion, then that goes into the tolerance value. So for example, around here, the grave rot series has a tolerance value of 3, whereas the Kalkaska sand has a tolerance value of 5. And what this is referring to is tons per acre per year that could be allowed to erode and still be tolerable. So what do you think about that? Does that raise some questions or some red flags to you? You think about that? If someone was telling you that it was tolerable for us to lose 5 tons per acre of Kalkaska sand. Yeah, what do you think?
Kalkaska sand is a pretty nutrient poor. Why would they be able to tolerate losing more than like?
That's a great point. That's a great question. So why is it tolerable to lose so much of this nutrient poor soil? And that part of that goes into the economics. So they're saying these Kalkaska sands, who cares? We can lose 5 tons per acre per year. And they're thinking, well, rates of formation, maybe that can keep step. However, there's been some pushback on this. So some of the state soil scientists have been saying, well, wait a minute. Is there any tolerable amount of loss? So let's just think a little bit creatively here. How would your opinion change if you worked for Trout Unlimited, for example? Is there any tolerable amount of erosion that you would want? No, not really. It doesn't, this equation or this statistic doesn't take into account any of the downstream effects. So it's only based on rates of formation. Other pushback that's come back more recently is actually coming from the geological fields. So some geologists have said, well, wait a minute here. It takes, if we're talking about a residual soil, not a transported soil, it takes nearly 100 feet of material to generate 1 foot of residual soil. In other words, you have to break down 100 feet of bedrock material and weather that through a process of thousands of years to make 1 foot of residual soil. There's no way that there's a tolerable amount of tons per acre per year that could keep step with that. So there's been a lot of pushback from geologists on this statistic. And then more locally, Mike Suka from the NRCS has said, wait a minute here, we've got to really temper this, even for transported soils. There's no way that 3 tons per acre per year would be a sustainable loss, even 5 tons per acre per year for Kalkaska sand. So I just wanted to caveat this statistic. Does it have utility? Yes. I mean, again, this is another thing that you can use to inform decisions, but there are some huge caveats associated with it. And one paper that I'll put up on Canvas that really, this is from the Journal of Soil and Water Conservation, it came out in the late 80s, was really pushing back on this, and they did a synthesis of where, I just wanted to read the conclusion, the last sentence of the paper, because it doesn't really pull any punches here. It says, policies, programs, and technologies cannot achieve the needed soil protection level if the performance standard is rooted in erroneous beliefs and institutionalized deceptions concerning the processes of soil development. There's no pulling any punches there. Furthermore, he says, acquiescence in unceasing soil resource degradation is not an acceptable public policy choice. So we know how he feels about the t-value. There's not a lot of ambiguity there. But it does have some utility and it's still used, you know, it still is provided in your county soil surveys. So any questions about that? Universal soil loss equation, K value, and the T value all have utility for predicting erosion and susceptibility to erosion. So a lot of the other tools that you have are actually going to vary quite a bit depending on where you end up working. So a lot of the rules and regulations are specific to local agencies. So Michigan DNR has its own guidelines. If you end up working in Wisconsin or Minnesota, you're likely going to have different guidelines. So I don't want to spend a whole lot of time on that because these rules will likely change depending on where you end up working. So for example, around here in the UP, where we basically have different flavors of sand, whether it's a loamy sand or a sandy loam, it's going to be glacially transported sandy stuff of one flavor or another, various types of moraines. What is likely going to be, based on that, what is likely going to be the overarching biggest rule of thumb governing susceptibility to erosion in our area? Slope. Yeah, so we can talk all we want about these nuances of texture class and how much clay is there, but around here, it's really going to come down to the slope class. So the letter that follows the number denoting the series on a soil map is really all you have to look at to understand susceptibility to erosion. And I provided in your handouts some of the other guidelines, and I provided all the sources. So from the Michigan DEQ, Michigan DNR, some various sources that you can point to if you need some justification for a management decision. And I don't need to spend too much time on it because the guidelines are pretty intuitive. Basically, if we have more fine textured soil and it's a steeper slope, it's going to have a higher susceptibility to erosion. And there are broad classes for that I provided in your handout. And the reason why this is important to consider is there was an EPA study done in Michigan in 1999, and they determined that from managed forests, 90% of the sediment comes from the road system that's generated in the forest system. So it's 90% of the sediment load is coming because of the way the forest roads are designed. So that's an important thing to consider. And the reason for that is the EPA doesn't regulate sediment exports from managed forests. I think I have a readout of it here. It's not under the purview of the EPA. So it's on you as a manager to take care of this. So if you're as an environmental professional, it's your job to try to mitigate erosion losses. The EPA is not going to care about it. Does that surprise you? Not really, right? I mean, it's not, sediments, it's not we've got bigger fish to fry. The government has bigger fish to fry apparently. But it's an important consideration. So these tools that you have for estimating erosion, that's what we have to deal with this issue. So any questions? Yeah, Kendra.
This is backtracking a little bit, but how do you calculate the t-value? Is there an equation or is it just based off a lot of data?
So this is a good question. How do you calculate the t-value? And these values are already generated. So this is something that's provided for you in the county surveys.
Okay.
And it's based, well, some would say it's based on sketchy data.
Yeah.
But it's something that at least you can say, hey, don't shoot the messenger. This is a tool that's developed by the county soil survey. That's what I'm using to justify my decision.
So every soil type has one?
Every soil type has its own t-value. Yep. So it's something that, and it's a good starting place. So based on the t-value, you might want to say, okay, well, that's a good starting point. I'd like to probe this a little bit deeper. Maybe I should use the Watershed Erosion Prediction Project, the WEP tool, to get a better idea of and see if you believe it. It's just a starting point for you to ask questions. Any other questions about those things? So I covered those really quickly, but I think it's because they're pretty intuitive. I mean, erosion stuff goes downhill, right? And I think it's fun too to think of the root of the word erosion comes from the Greek word rodera, and rodera is it's the root of the word rodent, right? and it means to gnaw. So when you think of erosion, you can think of a giant rodent gnawing away at the landscape. That's the root of the word. Any questions? So I want to leave enough time so that no one's stressing out about taking the quiz. I'll get those out.